All right, in today's lesson, we're going to be looking at compound interest and continuous compound interest. So for compound interest here, we have the following formula. This is P at t is P naught 1 plus I to the power of kt. Don't forget your I value is equal to your annualized rate of interest divided by k. So we're going to look at word problems involving these. And also in today's lesson, we'll look at the idea of compounding continuously as well. With this formula here that you see, the compounding is happening, either it happens daily, monthly, yearly, semi-annually. There's some fixed amount of time it happens per year, like a finite number of compounding periods per year, and then that's kind of partitioned up throughout the entire t years. Whereas with continuous compounding interest, which we'll look at that formula as well, you'll be computing interest continuously. All right, let's take a look at some of the problems. For the first problem here, we have a sum of $850 is invested for 10 years, and the interest is being compounded quarterly. At the end of this investment cycle of 10 years, you have $1,000 in the account. So right away, I know I'm using my compound interest formula because you're computing that interest not continuously, but in this case, we're computing interest 4 times a year for 10 years. So I go right to my compound interest formula. In this case here, k is the number of times you're going to compound per year, which is 4. We know that after 10 years, so p at 10 is equal to 1,000. I know P naught, my initial investment amount, is $850, and like we said, T is 10. In this case here, what we want to find is the annualized rate of interest. So sub this all into our formula, giving us. So subbing this all into the formula, we have the following. Again, we're looking to solve for R here, so I'm going to go ahead and divide out by that 850, and then take the 40th root to try to isolate this variable of R that we want to solve. After this, we're going to subtract 1. And getting this down to a decimal place, we have R over 4 is approximately equal to 0.0040712. Multiplying across by 4, we can solve for R, and we get R is approximately equal to 0.1628, and expressing that as a percentage, we get approximately 1.62%. So in this case here, the annualized rate of interest is 1.62%. Let's now take a look at the idea of compounding continuously. So when we talk about computing interest continuously, let's first focus our attention on our compound interest formula. In this case here, I substituted the I with the R over K. Now what we're doing here is we're focusing on 1 year. So we're going to let T equal 1, so you don't have that exponent of T here. Now what we're going to do is I'm going to rewrite R over K as 1 divided by K over R. And you'll see if you multiply by the flip, you'll get the R over K back. I'm going to go ahead here and raise this to the power of K over R, and then multiply that by k. And you'll see here, by doing so, power to power you multiply, the r's will cancel, and I'll just be left with an exponent of k as to what we just had. Now what I'm going to do here is I'm going to let h equal k over r. So just get rid of this k over r, replace it with h's, and now we have the following expression. Now you'll notice as k goes to infinity, it must also be the case that k over r will also go to infinity. So as the number of compounding periods, recall, K represents the number of compounding periods used per year. If I go from yearly compounding periods to semi-annually to monthly to daily to by the minute to by the second, etc., as K approaches infinity, we end up computing interest continuously. Well, as K goes to infinity, so must too will be H. K over R would also go to infinity. So because of that, what happens is this expression here is exactly our definition of E. Therefore, as h goes to infinity, the following expression right here, 1 plus 1 over h to the power of h, that is the exact definition of our natural base E. So therefore, this formula becomes such that A will approach P times E to the R. So therefore, by taking our compound interest formula and letting K approach infinity, we generate our base of E, and our formula for the amount at the end of the investment will be equal to P times E to the R. This is obviously for 1 year. Again, just to remind you, we had let that investment T equal 1. And by doing so, we now have that the amount at the end of that 1 year, if you're investing continuously, is equal to P times E to the R. Notice here that as you increase the compounding periods, you have to increase the amount of money that you're making at the end of that investment cycle. And generally, you have that P times 1 plus R over K to the power of K must always be strictly less than P times E to the R, right? And what that means is that the amount of money that you're going to make investing for 1 year when compounding k times per that year will always be less than the amount of money you'd make with the same annualized rate of interest investing continuously for that year. So what you have here is no matter how frequent the compounding amount in that year happens, the P to the R is a ceiling, like an upper bound to the amount of money that you can make. Let's summarize our work and look at the continuous compound formula. So continuous compound interest can be expressed as follows. P at t, the amount of the after t years, is going to equal your initial investment amount times e to the kt, where k is your growth rate and t represents the number of years that you are investing. All right, now that we have our compound continuous formula and our compound interest formula, let's take a look at some word problems. These will be all mixed together. Some will be compound interest, some will be continuous compound interest, and we're going to decide when do I use my compound interest formula versus my continuous interest formula and what those problems look like. Let's take a look. So for our first problem here, we have $50 is invested at 6% compounded monthly for a period of 3 years. So right away, this is our compound interest formula. This is not continuous. They would have had to tell us in the question that interest is being computed continuously. We can see here that within a given year, it's being compounded 12 times monthly. So that's a fixed finite number of times it's being computed per year. And again, with continuous interest, that would happen infinitely many times within a given year. So take a look at our compound interest formula, subbing our numbers in. So take a look at our compound interest formula. I get P at t is equal to 50, that was my P naught value, times 1 plus our annualized rate of interest of 6% divided by monthly, that's my K value, is 12, to the power of what? To the power of 12 times 3. 12 represents the number of times that I'm computing interest per year. I'm doing that for 3 years, so that's 36 times. Going ahead and simplifying, we get the following. And our final answer comes out to be P at 3 is approximately equal to $59.83. All right, let's look at another problem. In the next problem here, we want to know how much money will result in $40 being invested at 7%. This time we're compounding continuously. So you can see here I went right to our compound continuous formula. I know my P naught value here is $40. I know that my growth rate is 7%, so I can write that as 0.07, and I know that T is 3. Subbing this all in, we get the following. 40 times e to the exponent of 0.07 times 3 gives me this value here, and getting that to 2 decimal places, I get $49.35. Let's take a look at another example. Must we invest to have $1,000 after 1 year at 12% compounded continuously? So right away, they use the phrase compounded continuously. Go right to your compound continuous formula. Going to that formula here, you see I went ahead and they tell me that we have $1,000 at the end of 1 year. So that's going to be P at 1. So in this case here, I know P at 1 is 1,000. Therefore, T equals 1. My compound interest rate was your K value. That's my growth rate. So that'll be 0.12. And we're looking to find that initial amount. So you can see here, I went ahead and divided out. We're looking to isolate and solve for this P naught. So I went ahead and divided that out. End up getting here, P naught is $886.92. So again, if you want to have $1,000 after 1 year, if you're offered a 12% compounded continuously rate, you only have to invest $886.92. At what interest rate must be compounded annually to double an investment in 3 years? So right away, it uses the phrase compounded annually. So within a given year, interest is only being calculated a finite number of times, in this case 1. So this is a compound interest formula, not continuous. So we have the following formula. And in this situation here, what they're saying is they want that investment to double. So I don't know what my initial investment is. I know it's just P naught, but I know I want that investment to double. So the only thing I have to do is let P at T equal to P naught. And by doing so, you'll see the P naughts cancel. And again, like we said, I sub that all in. You're going to end up getting your cancellation here. Then we can go ahead and isolate for R. And you'll see here, as discussed, these P naughts cancel. You're left with the following equation. And then went ahead and took the third root of both sides of the equation, giving us 2 to the power of a third equals 1 plus R. Subtracting R, you get it. This is the exact value of R, is 2 to the power of a third minus 1. As a decimal place, we get approximately 0.2599. And so that gives us an answer of approximately 26%. So therefore, what you need to double your investment in 3 years, you would need to be offered a annualized interest rate of 26% compounded continuously. So you would need a 26% annualized interest rate in order to double your investment in 3 years. So for the next question here, he has Angela has $100 to invest at 10% per year, compounded monthly. How long will it be before she has $175 in the account? Then the second question says, if we're compounding continuously, how long would it take? So comparing the two situations. So let's take a look and see. So you notice here on the left-hand side, I went ahead and did the compound interest formula, assuming you're compounding monthly. At the end of the investment cycle, we have 175. We start off with $100. The interest rate was 10%, compounded monthly. And again, we want to solve for that t value to see how long it takes to actually get the 175. Going ahead, dividing by 100. Then I went ahead here, and to solve for this t value, I had to take the log of both sides. So when you take the log of both sides, this 12t will drop down, and that's what you see right here, the 12t dropping down. I then went ahead and divided across by the log of 1 plus 0.10 divided by 12, sort of isolating for that t value. And getting that right-hand side down to 2 decimal places, you get 12t is approximately 67.43. Dividing across by 12, I get t is approximately 5.62 years. All right, now let's take a look at this exact problem if we were computing interest continuously. All right, taking a look at our compound continuous formula. Here I went ahead and we wanted to finish with 175. We started with 100. We had a growth rate, or the interest rate was 0.10, 10%. I then went ahead and divided by 100. Took the ln of both sides. After taking the ln of both sides, this exponent will drop down. Ln of e, as you know, is equal to 1, so that goes away. I then went ahead and isolated for t. Getting this down to a decimal place, I get 5.6 years. So you can see here, comparing these two results here, the change is so very slight. I have 5.62 years compounded monthly, and then 5.6 years compounding continuously. The change would be more drastic perhaps if we were compounding quarterly or semi-annually or even just annually, but since we are compounding 12 times in a month anyways, they are fairly close, but you still will hit that rate quicker, hit that 175 quicker by compounding continuously. Let's take a look at another problem. So for the question here, we're going to take a look at the idea of inflation. And with this question here, you have an inflation rate of 3%, and they're asking you how much will $1,000 in purchasing power be in 2 years. So the idea here is every year you're losing 3%, or in other words, you're being left with 97%. So on year 1, it's just going to be 1,000 times 0.97. Then you're going to take that amount of money, and then on year 2, you're going to multiply again by 0.97. And then lastly, on year 3, you're going to again take that new amount you have and multiply by 0.97. That is all equivalent to just raising that all to the power of 3. And if you do that, you end up with $940.90. All right, let's take a look at one last problem. So for our final problem here, they give you this formula. This formula is t is ln of m divided by n times ln of 1 plus r over n. And what's going on here is this is used to calculate the number of years, t, required to multiply your investment by a factor of m, given a fixed rate of interest r and number of compounding periods n. So in this example here, what's going on is you are told that you want to double. So we want to double my investment. That's going to be my m value. I want to double the investment. We're compounding annually, so my n value is equal to 1. And my rate of interest here is going to be 12% or 0.12. So subbing all this into this formula here, it'll tell you how many years it'll take you to, in this case, double your investment if you're compounding annually and at an interest rate of 0.12 or 12%. So again, summing all these numbers in here, we get the following. Simplifying, I get ln of 2 divided by ln of 1.12, which is approximately 6.12 years. So I just thought I'd show you guys this formula here. This is just something different, another way of expressing the number of times it'll take you to like double, triple, quadruple an investment. This would be something ideal to put in a spreadsheet. Maybe you have this equation, you have these variables that can be changed in the spreadsheet, and you can quickly take a look at changing the m to a 2, a 3, a 4. And as you adjust those variables, you can see how long it takes you to achieve a growth rate of a factor of m. All right, that concludes today's lesson on compound interest and continuous compound interest.